Hello, and welcome to this webinar presented by Radiant Vision Systems. And now I'd like to introduce today's presenter. With us today we have Chad Green, the Software Quality Manager, coming to us from Radiant Vision Systems. To read more about Chad, please look at the speaker bio window right next to the main presentation window. And Chad, welcome to today's event. And with that, I will pass things along to you to get started.
Thanks for hosting this. I'm very happy to be here today. My name is Chad Green, and I'm the Software Quality Manager at Radiant Vision Systems. As you can see, I've written a bit about myself here, but I won't read all of that. Instead, I'll just offer some highlights. My background is in engineering and physics, and I have a passion for understanding and for measuring how light impacts how we perceive the world. Indeed, something that I enjoy staying up to date on is the latest research findings regarding how blue light impacts our health and well-being. Throughout my career, I've been fortunate to work in science-based institutions and companies, and my presentation today reflects that. I've been working in the domain of light metrology for 13 years, and have been working at Radiant for 2.5 years, where my focus is directed toward the quality of our light measurement systems. And what do we do? Radiant creates light measurement solutions and tools that are used to inspect millions of display devices every year at many of the world's leading consumer electronics, automotive, and AR/VR companies, all of which are supported by our sales and engineering teams in North America, Europe, and Asia. Now, today we will begin talking about display metrology, why we measure displays and what we're looking for. Much of what I'll cover is broadly applicable to most displays, including today's standard flat panel displays found in devices such as laptops, televisions, and smartphones. Then we'll take a look at some unique measurement challenges that apply to specific types of displays, like AR/VR devices, newer emissive display panels like OLEDs, and others. All display devices are designed to be viewed and used by humans. So the standard for measuring visual quality of a display is, how will it be seen or perceived by humans? Displays play a critical role in our day-to-day lives, being viewed many hours of the day, from phones to laptops, to TVs, to the dashboards in our cars. Whether we are aware of this or not, we, as consumers, expect perfect, defect-free displays to maximize our immersion into devices and minimize any distractions while we are interacting with displays. Anything short of that can result in returns and complaints, which are detrimental to the companies or brands that produce the displays. Display metrology is the science of display measurement. Like any science, both a standard and a reference guide display metrology. In this case, we apply standard principles outlined by the CIE, or the International Commission on Illumination. The CIE is an authority on light, and for nearly a century they've provided methods of calculating light values and metrics based on a reference model. The reference is human vision. The CIE's methods of quantifying measurements is derived from studies of the visual response of a standard human observer. We calculate the perceived output of a display based on the standard human eye response to visible wavelengths of light. How we measure our perception of or visual response to light can be broken down into two parts: photometry and colorimetry. Photometry is the science of measuring light perceived by the human eye, and it is often loosely described as how we measure how bright something is. Colorimetry is the science of measuring color perceived by the human eye. Both colorimetry and photometry share a very important commonality: to measure as perceived by the human eye. Human visual perception ultimately determines our experience of light, including the accuracy and appearance of colors in devices like light sources or displays. It makes sense, then, that the objective in testing displays is to measure light and color in the same way a human perceives them, to ensure that the visual quality of a display matches human experience. By obtaining values standardized against human perception, we can enable automated display metrology with meaningful results. To evaluate displays, we need to understand two fundamental aspects of light: the light output produced by the display, and the light input we receive via our human visual system. Let's start with the light output from the display. Our eyes are sensitive to different wavelengths of light in terms of color and brightness. In low light levels, such as evening darkness, our rods perceive brightness but not color, and they do so with low spatial acuity, meaning that they allow us to sense that objects are in our environment, but we might not be able to discern any fine details of those objects. In higher light levels, such as daytime brightness, this sensitivity comes from our eyes' cones. We have three types of cones: short, medium, and long, each of which are sensitive to a specific range of wavelengths. In the graph in the lower right is a rough illustration of the normalized response of each of our eyes' cones. This shows how powerful we perceive each wavelength to be. The short cones, denoted as the blue curve, are named due to the short wavelengths of light that they respond to. The medium and long cones, denoted by the green and red curves respectively, are similarly named. It is important to note that the cones in our eyes can't detect individual wavelengths. Instead, they see the sum of the total light within the wavelength regions that each are sensitive to. This can be understood as the area under each of the curves in the graph. Understanding this visual response, which is called our spectral sensitivity, helps us understand our perception of brightness and color of various light sources, including displays. The standards body we mentioned previously, the CIE, provides a method for calculating photometric and colorimetric measurements. Based on studies of standard human visual response, the CIE derived color matching functions, or curves, one for each of the three values that are combined to create a perceived color, similar to our eyes' cones. These functions weight an input value of light and allow it to be measured in terms of human visual response at each wavelength. Because this method provides three values, one for each area under the curve, outputs are commonly referred to as tristimulus values. A combination of the three X, Y, and Z tristimulus values are used to measure color. As we see in the table, CIE 1931 provides formulae to calculate lowercase x and y using uppercase X, Y, and Z. In CIE, this measurement is chromaticity, and X, Y give us a chromaticity coordinate. Now let's talk about the output of light sources and how they interact with these CIE curves to give us standard luminance and color values. Here is a basic example. The large rainbow is the spectral power distribution, otherwise known as the SPD, of sunlight, which is its absolute power per wavelength. The curves represent what we actually see. If we want to measure how we perceive a display, how bright it is or what color it is, we need to measure its light output using a method that derives values based on a model of our spectral sensitivity. To determine the perceived color of the sunlight, we perform the following steps. First, we multiply the spectral power distribution of the sunlight with each of the spectral responses of the human visual system. Second, we then calculate the area under each curve which resulted from the multiplication in the first step. These areas are denoted uppercase X, Y, and Z, and are referred to as tristimulus X, Y, and Z. Finally, we calculate the CIE 1931 chromaticity coordinates xy, or as labeled here, Cx and Cy, as the division of the tristimulus x and tristimulus y values by the total sum of all three tristimulus values respectively. Because sunlight contains visible light across all wavelengths, the resulting chromaticity coordinate points to it being mostly white, as shown in the figure to the right, which is known as a color space or chromaticity diagram. Now let's look at an example which is closer to displays, a blue LED. The spectral power distribution for this blue LED example is very narrow, with emission only in the blue region of the visible spectrum. Following the same steps as before results in a small chromaticity X value and an even smaller chromaticity Y value. When plotted on the CIE 1931 chromaticity diagram, the chromaticity for the blue LED clearly lands in the blue region. This should make sense since the spectral power distribution for the blue LED did not contain any light with wavelengths that are significantly detected by the X or Y color matching functions. To summarize, the steps we took in the previous two examples can be mathematically written as integrals of the spectral power distribution of the light source, first weighted by each of the color matching functions. Not yet mentioned, but important to note, is that tristimulus Y uniquely determines the luminance of the light source. The CIE color space encompasses all color sensations that an average person can experience. The color space or chromaticity diagram represents all colors that the average human eye can see, but just because those colors can be perceived by the average human eye does not mean that all technologies can produce all of the possible colors that the average eye can possibly see. Producible colors are within the triangle limit, known as a color gamut, and the points of the triangle meet at a pure color apex, which consists of three primary colors. All other colors within it are a blend of these colors. The Planckian locus, the black line, defines another metric called correlated color temperature, or CCT. The lower the CCT of a light source, the warmer it is said to feel. Conversely, the higher the CCT of a light source, the cooler it is said to feel. It is worthwhile noting that correlated color temperatures are measured in units of Kelvin, where 10,000 is a very cool color temperature, and 2000 Kelvin is a very warm color temperature. Circling back to the triangular region in the chromaticity diagram, the shapes of color gamuts are driven by the physics behind the emissions from the light source. In the display industry, new color gamuts are being created all the time as technology advances. Applying standard measurement principles is really important when we start getting into quality control applications. Colorimetry gives us a measurement tool that quantifies the value of what we visually perceive. For example, as a display manufacturer, I want my display to have a gamut that includes this color blue. Ensuring that all of my displays achieve this color blue ensures that my customers will have the intended visual experience. But what is this color? Colorimetry enables me to assign a numerical value to this color and set pass-fail tolerances. The values that colorimetry provide are also standard values because they are based on universal scientific measurement principles, functions, and formulae from the CIE. Having a standard value means that no matter what, where, or when I'm measuring, I'm going to be using the same scale and getting repeatable measurements from device to device. I can set a tolerance not only for displays manufactured at one facility, but for all displays manufactured across all of my facilities, no matter where they are. Standard values can also be understood by everyone. We now have a common mathematical language to use when we talk about color. Instead of telling my panel supplier, "Look at this blue. I need you to match this blue for all of the panels you supply to us," I can tell my supplier, "I need panels with CIE chromaticity value 0.1 in the x-coordinate and 0.15 in the y-coordinate." My supplier and I can both use colorimetric instruments to verify that this value is correct throughout all manufacturing, OQC, and IQC processes. Next, we will talk about some different properties or characteristics of displays that are often measured to evaluate display quality. I've already talked a lot about luminance or brightness and color. These values can also help us determine, is the display bright enough? Is it producing the right color? Does it meet gamut specifications, such as the whole range of colors that the display can produce? What's the contrast ratio? How uniform are brightness and color across the display? Are there any defects, such as dead pixels, bright pixels, dust? Are there unacceptable luminance or color variations at different viewing angles? And so on. These qualities are a product of the light that the display produces. For this reason, display metrology fundamentally relies on measurement of light. Here are some display quality examples. Contrast is measured as a ratio of the luminance between dark and light regions. We often use a checkerboard pattern test image to perform this analysis. The concept is pretty straightforward. We measure the luminance of the white squares and the luminance of the dark squares, and then give the ratio. We can also perform this test at different brightness states of the display. If a contrast ratio falls within acceptable tolerances, we can accept the display. Another display quality example is uniformity, described as the lateral variations in brightness and color values. Like contrast, we can measure uniformity by comparing measured values of luminance and chromaticity. In this example, we show uniformity analysis based on ANSI brightness, a metric defined and published by the ANSI standards body, which compares equidistant measurement points across the display. Discrepancies between each point allow us to determine if the uniformity falls within specified tolerances. Uniformity is often measured with an imaging-based device, which I'll talk more about later. Defects in a display are typically random and vary in shape, size, or severity. These include dot defects. These are stuck on, dead, or dim pixels. They can be contaminant particles at any point in, on, or under the display glass. We also have line defects, and these are connected rows of dead pixels or sections of dim or bright pixels. These typically extend in the vertical or horizontal area of the display. And finally, we have mira. Mira is Japanese for uneven, and it describes an area of non-uniform brightness or darkness at any point in the display. Interestingly, mira can take on a lot of different forms, depending upon the cause. For example, defect or stress in one or more layers, non-uniformity in the bonding, cleaning wipes or fingerprints, particle inclusion, scratches, fibers, or a backlight non-uniformity. There may also be mira created by light creeping around the layers, leaking in from the edges. You can also have mira resulting from pressure applied by the display casing. And of course, any stresses applied by deformation of the display module can lead to mira. Another commonly measured display property is view angle performance. View angle measurement shows us how brightness color, and contrast vary as our eyes perceive the display at an angle. This is an important characteristic to measure in large and fixed position displays where the display angle is not easily adjusted for the position of each viewer. For instance, TVs, monitors, or integrated displays like in automotive dashboards. Measuring view angle is traditionally done the same way we view the display, by measuring the display quality at each angle. Our next section is about the different types of instruments that can be used to measure light and color. Various types of light metrology instruments exist for measuring displays, such as luminance meters, spot colorimeters, spectroradiometers, and imaging colorimeters. Each of these instruments has different strengths and limitations that we'll look at in the next few slides. One big differentiator between metrology tools is whether it is a spot or imaging system. A spot measurement system measures a small area of a luminous scene. The size of the spot will depend upon factors such as the size of the aperture, the focal length of the lens, and the separation distance between the measurement system and the scene. An imaging measurement system can be thought of as many spot measurement systems assembled in an array-like configuration. The benefit of an imaging measurement system is that it can often measure the entire extent of the display in one measurement. We can also compare these metrology tools by looking at the way they measure color. Colorimeters use a filter-based system. The imaging colorimeter typically uses color filters with transmissions that match the tristimulus curves we discussed earlier in the presentation. This allows us to accurately measure color as perceived by the human eye. Spectrometers break up light into its components so that we can get the entire spectral power distribution. The spectrum of test equipment extends from the lab to the production line. We see the challenge of in-line inspection tackled from both ends. On one end, we have highly scientific display metrology systems, like spot meters and spectroradiometers, that capture standard CIE measurement values of light, like luminance, chromaticity, and spectrum, all of which are key metrics for understanding the visual quality of a display. On the other end, we have imaging systems like imaging colorimeters and machine vision cameras. The original system designed for light and color measurement was a meter that relied on measurement of a single spot on the display at a time. A classic example is a spot meter called a spectroradiometer. This instrument is highly accurate. It captures a very narrow sample of light and uses its internal components to split the light into its unique wavelengths, so we can calculate the precise power per wavelength. A spot meter can be used for brightness, color, contrast, and uniformity measurements. Although these systems are applied in production applications, they have the classic disadvantages of a traditional metrology system. If only one spot on a display can be measured at a time, we need to think about how many spots to capture and how to position the meter at the appropriate or representative locations several times for each display. This is time-consuming and has possible repeatability issues, and thus a risk for error. We also aren't getting a complete picture of the data output from the display at once. So this instrument is limited when it comes to other measurements like defect detection. Imaging is extremely useful for display testing because we can capture all areas of the display at once to understand contextual information. Without imaging, it becomes difficult to measure uniformity or changes in brightness and color across a display. It also makes it virtually impossible to ensure that we capture all defects that may be present in the display area. Depending upon an imaging system's resolution, we could capture several tens of millions of data points at once to compare and detect anomalies. Let's look at some examples of display tests that imaging systems can perform. Brightness and color offset, or measures of the luminance and chromaticity of the display at its current setting. Non-uniformity, measures if the luminance and color is the same everywhere across the display if the display is intentionally configured that way. Pixel and line defects, locates pixels which may be stuck on, dead, or not achieving their required state per the current display setting. Sparkle notifies of the phenomenon where the light from pixels is being refracted in a complex manner by layers of optical material above them, thus appearing to sparkle under certain conditions. Light leakage measures, for example, when the light from LEDs in an edge-lit display scatters into the observable display area in an unwanted manner. Mira, as discussed earlier, measures undesirable regions of unevenness in the display active area. Image sticking measures when the display is unable to completely erase the previously shown image before presenting the next image, which is a display refresh problem. And view angle measures the perceived emission qualities of the display at various angles of observation. Just like our standard display tests, we test for defects using the same algorithms, but apply them to different areas that are captured by the imager. We are able to identify and grade these defects in any manifestation of the image display, regardless of shape. Defects come in a variety of shapes and sizes. For example, each type of Mira has its own characteristics and requires a specific algorithm to detect, identify, and test for it. There are often several types of Mira present in a display, so it's helpful to have analysis software that can identify multiple types. Here, we show a few images with Mira analysis performed. In reality, there are many other types we could identify and analyze across a display. We've talked a lot about hardware today, but another key element of efficient quality testing of displays is the software you use for testing and analysis. Ideally, a robust display metrology software will provide automated test sequencing for rapid data capture and analysis, a library of standard and application-specific analyses, such as AR/VR and HUD, pass-fail determination based on user-defined thresholds, a user-friendly interface, and integration with production control systems. As technology has evolved, there are so many different types of devices and applications that now use displays. As powerful as many metrology instruments are, special optics, form factors, and sophisticated software are now needed for different measurement scenarios. In this section, we'll look at some of those unique measurement challenges and applications. The first challenge is how to measure displays that will be viewed from multiple angles. In settings where a screen is viewed from multiple positions, view angle is increasingly important. For example, the navigation infotainment screen in an automobile needs to be usable for both the driver and the passenger. Traditional systems for view angle measurement apply rotation to position a photodetector and display at a range of angles relative to one another. Here we show two examples. A fixture where the photodetector is rotated around the display, and another where a two-axis goniometer rotates the display relative to the detector. Either method captures very comprehensive data, but setup time, equipment size, and complexity can be high. Maybe this is okay for the lab and R&D applications where we're concerned with data and exploring test methods, but we need a more efficient solution for the production line. One way that this challenge can be addressed is through the use of a conoscope lens, which uses Fourier optics to transform a directional distribution of light rays emanating from a single point to a lateral distribution of light rays. Using an imaging photometer or colorimeter with a conoscope lens means that we capture data for a range of view angles in a single measurement. There is no need to rotate the detector or the display, and we are leveraging an easy-to-use add-on to existing cameras. For an example, these images show angular light distributions captured with our flat panel display conoscope lens. Careful inspection of the data shown for the monitor reveals subtle differences between white and red display settings and green and blue display settings. Larger differences are apparent when comparing either white or red display settings to green or blue display settings. Even more prominent are the differences in the data when a privacy screen is added to the monitor. Note that the purpose of the privacy screen is to make the content shown on the monitor less visible to observers to the left or right of the monitor, while maintaining the ability to show content to an observer directly in front of the display. As shown in the figures corresponding to the monitor with a privacy screen, less light is being measured at wider angles when the privacy screen is in place. This next section will speak to challenges with evaluating the quality of visual experiences inside the wide array of near-eye displays, now referred to as extended reality devices, encompassing augmented, virtual, and merged reality systems. Near-eye displays present a ton of additional challenges that we don't need to consider with traditional displays because near-eye displays are viewed extremely close up, viewed with a wide field of view, viewed within head-mounted devices, and viewed on a transparent substrate with background ambient light. But there are a few things that metrology systems must keep in mind for any artificial, virtual, or mixed reality device. It comes down to the fact that all systems used for extended reality, or XR display evaluation, must account for visual elements produced by the device as perceived by the user. The XR display is the combined visual elements produced by integrated displays, projection units, and associated optical modules within the device. The quality of an XR display is dependent upon a user's perception of the light relayed from the display over a spatial area. User perception is influenced by parameters under which these displays are viewed, which is near to the eye, within a headset, and across an angular field of view. XR display test systems should replicate the viewing conditions of the user as much as possible in order to ensure accurate qualification. Extended reality displays are viewed near to eye. The headset eyepiece, or exit pupil, is usually positioned 10 to 20 millimeters from the intended position of the user's eye, itself referred to as the entrance pupil. Mimicking human perception results in a few specific requirements for AR/VR metrology systems, such as the aperture entrance pupil should mimic the size of the human pupil, which is approximately 3 to 5 millimeters in diameter, to receive the equivalent light as the human eye. The need to measure within the headset at the same position as the human eye without occlusion, and the lens needs to capture a wide field of view to mimic the human field of view. Our goal is to match the intended entrance pupil position within our imaging system's entrance pupil. In imaging lenses, the aperture acts as the entrance pupil of the imaging system. While it may be possible to fit a standard measurement lens within an extended reality headset, it's extremely unlikely that this lens will capture the full field of view as seen with the human eye. This is because the aperture of a typical imaging system is buried inside the lens housing, as shown here. The resulting image captured by this lens will be a clipped view of the display beyond the exit pupil of the headset. This is something called the knothole effect. The effect is like viewing a scene through a knothole in a fence. When the eye is positioned at the hole, the full field of view can be seen beyond the fence. As the eye moves away from the hole, the view becomes occluded by the edges of the fence. Standard optics like this lens, with internally integrated aperture, do not capture the full display field of view beyond the device entrance aperture, because the lens hardware prevents positioning the camera aperture at the human eye position. However, lenses designed for measuring AR/VR devices need to use an optical design that positions the camera aperture at the front of the lens at the same location as a human viewer's eye. This lets the camera capture the full display field of view beyond the AR/VR device aperture to be captured without occlusion by the headset hardware. For example, Radiant's specialty AR/VR lens and XRE lens capture the full display field of view within AR/VR headsets, primarily by replicating the human eye in terms of pupil size, eye position, and binocular field of view. Emissive displays such as OLED and micro-LED displays are susceptible to wide variation due to the fact that they are made of many individual emitters. When each emitter is a separate LED, pixel-to-pixel non-uniformities become more common with issues such as dead pixels or hot, overly bright pixels. Correcting non-uniformities means first being able to measure and characterize the pixel-to-pixel differences in luminance and color. Manufacturers need to not only measure, but also to correct these defects to increase production yields. Each pixel of an OLED is an independent emitter as shown in this image. What we mean by pixel is any of the red, green, or blue elements which combine to form the bright dots in this image. OLED displays require us to evaluate each pixel for failures. During the manufacturing process, things can go wrong. Bad pixels, dead pixels, and non-uniform pixels can exist that are hardly detectable by human inspection processes. Compared to previous technology, LCD has a backlight and unique filters to show the color and luminance. This is not the case for OLED pixels. They exhibit pixel-level variation, color dependence on brightness, and non-uniformity known as mira at low gray levels. Measuring pixel-level variation for today's OLED and micro-LED displays typically requires a high-resolution imaging system and a microscope lens. For example, the Radiant Prometric Imaging Colorimeter and 20x microscope lens was used to measure the display pixels shown in the images here. By measuring each subpixel, we can calculate correction factors and send them to the display driver to restore uniformity. This is a process called demura. Issues may still exist after correction. This is because the correction factors are bounded by the worst pixel in the device in terms of choosing a target. It's always a trade-off between sacrificing luminance and getting a better correction. In the example here, targets were chosen that met stringent non-uniformity criteria. Thus, the uniformity is better after correction. Transparent displays present some unique measurement challenges because images are projected on a transparent surface that the user can see through. One type of transparent display are HUDs, or head-up displays, in automobiles and aircraft. Transparent television public signage is becoming more common. For all of these see-through displays, quality challenges exist due to the background environment also being visible through the display. and because of the variable ambient light conditions. With these displays, what is of the greatest concern, and thus the most challenging to assess, is their contrast and legibility and safety and visibility. Taking the example of HUDs, or head-up displays, measuring the display requires an imaging system that can evaluate brightness and contrast against an ambient scene, and be able to locate images projected at variable depths or locations. In automobiles and airplanes, it's also important to ensure that display performance meets industry regulations and standards for visibility and safety under all operating conditions. One important measurement for head-up displays is being able to determine the projection distance. How is this accomplished? Calibrated imaging systems can provide absolute distance measurements. A calibrated imaging system with an electronically controlled lens can determine the projected image plane for the HUD, which helps to remove human calculation and error and reduce the time to set up measurements. Here is another use case where using an imaging system is key. Imaging all data points in a single image also allows us to determine accuracy based on context. Context is required in all of these examples to evaluate the accuracy of given points in the projected image. Now, as I close out this presentation, I'd like to summarize both the insight we can gather from performing sophisticated display tests, as well as the benefits that can be gained by using modern display testing systems. Following this, I'll field some questions from the audience. To reiterate the importance and benefits of display metrology, it is critical to understand that it ensures the intended performance of a display device. It pinpoints and quantifies quality issues and defects. It allows pass-fail determinations to be automated against a consistent standard from device to device, line to line, and supplier to supplier. It enables manufacturers to increase yield, and it maintains customer satisfaction. To wrap up, as we've seen, the principles that govern display metrology are intended to provide a very accurate, scientific approach to quantifying the display's output. Measuring displays demands a scientific approach and systems to capture and quantify objective, accurate values. Imaging photometers and colorimeters meet a range of measurement and inspection applications. With quantifiable inspection data based on human visual perception, process improvements can be made to ensure quality that accurately reflects customer experience. And with that, I believe that we now have time for some questions from the audience.
Thank you so much for that great presentation. And now we're going to be moving into the Q&A session. We do have some questions that have come in from the attendees, so we're going to move into answering those right now. Now for our first question.
Our first question from the audience asks, is there any recognized standard used by display manufacturers for measurement? That's a good question. Yes, there are various standards, especially in automotive displays and avionic displays, and even things like phones and tablets. ANSI is one such organization that I mentioned earlier that produces such standards. Other standards I think that come to mind, and for which I have been an active contributor, are the IDMS, or the Information Display Measurement Standard, which is published by the ICDM, or the International Committee for Display Metrology. And there are various other standards published in the automotive and avionics domains by the SAE, or the Society of Automotive Engineers. So please feel free to contact me for more information about any of these, and I'd be happy to point you in the right direction. And we have another question from the audience, which wonders, does your imaging system need to have the same resolution as your display? And what are the typical resolution requirements? Okay, well, that's a tricky question, but I think the short answer is it kind of depends on what you're trying to do. For those emissive display applications we talked about, where we need to accurately quantify each individual emitter on an OLED or a micro LED, then having really high resolution is important. We want to be able to maximize the number of imaging system pixels to the display pixels. So perhaps we want to have 5 or 10 or more imaging system pixels for every single display pixel. Thus, we need high resolution for that type of application. But if you're looking at doing something like basic uniformity testing, where we don't actually need to see every single pixel, then much lower resolution may be acceptable. And we have a third question from the audience, which asks, what's the brightest resolution image that can actually be captured in a production measurement system? Well, that's a great question. We actually use high dynamic range imaging solutions that are based upon a technology that's called electronic bracketing. And that allows us to expand our fundamental measurement range through sets of composited exposure times. And then on top of that, we can also extend the measurement range to even greater than 1 million candela per meter squared by applying the right neutral density filter in front of the sensor. So these are all of the things that Radiant can support and evaluate with the end user to understand what their overall needs are. One of the things I didn't highlight earlier is that in our I-series imaging colorimeter, we actually have a built-in neutral density filter wheel. This neutral density filter wheel can automatically apply the right neutral density filter, such as an ND1 or 2 or 3 or higher, to ensure that we get the appropriate dynamic range necessary for measuring extremely bright light sources. So thanks for that question. And hopefully we have time for a fourth question from the audience. They would like to know, do you need chromaticity information for DiMera, or is luminance sufficient? Is it corrected for both color and intensity on the pixel level? Well, that is a very interesting question. Traditionally speaking, DiMera has been done with a photometric camera, or what we call a photometer, which doesn't necessarily rely on the color component. We can produce display DiMera corrections based upon the luminance channel itself. However, as display technologies are changing, we do have customers who are now working with us on color DiMera solutions. I would say that if we were to go back a few years ago, we were primarily focused on the photometric side for correcting DiMera based upon the luminance channel. However, of course, with the changes in display technologies and the advances that are being made so rapidly, we are also evaluating color DiMera as well.
Great, thank you. And that was our last question, so we are going to wrap things up right there. So once again, Chad and the entire Radiant Vision Systems team, thank you so much for the great presentation. And thank you, Chad, for answering some of our audience's questions today. And of course, we'd like to thank our audience members for being part of this webinar event. Take care, and we will talk with you soon.